Hi everyone, I'm Shouvik Choudhury. I'm a distinguished postdoctoral fellow at the Academia Sinica Institute of Astronomy and Astrophysics in Taipei and Taiwan. And I'll talk about cosmology in an extended parameter space, new constraints on dark energy and neutron masses with DESI baryon acoustic oscillations data. My talk is based on these two papers. The first one was published in the Astrophysical Journal Letters, and the second one has been accepted in the same. The first one uses DESI DR1 BAO data, whereas the second one uses the DR2. In our cosmic evolution, we have radiation, matter, and dark energy, and radiation is composed of neutrinos and photons in the early universe, and matter is constituted by cold dark matter and baryons. Whereas in the late universe, neutrinos contribute to the matter density when they become non-relativistic. Now, in the early universe, we had radiation-dominated era, but radiation energy density falls off at a faster rate than the matter density, and we had matter-radiation equality at the redshift of around 3,400, and then the matter-dominated era started, and currently we have dark energy-dominated era close to the present universe. Now, dark energy remains subdominant for most of the evolution of the universe if we consider a cosmological constant as shown in this plot here, where the energy density is constant. But this dark energy density can vary, and if it varies, then we would be interested in the variation in the late universe. And hence, we can parameterize dark energy in this way, as you can see on your screen, in this W0W parameterization or CPL parameterization. So DESI in last year, April, gave the result that the cosmological constant, which is W0 equal to -1 and W equal to 0, this cosmological constant is rejected at 2.5 to 3.9 sigma, depending on the supernovae datasets used. So DESI used the DESI DR1 BAO data combined with CMB data from Planck and also CMB lensing data from Planck and Atacama Cosmology Telescope, along with 3 types of supernovae data from Penton plus Union 3 and DESY5. So the strongest constraint of 3.9 sigma rejection of cosmological constant was given by the DESY5 data, which is given by the green contours, whereas Penton plus gives the most relaxed constraint of 2.5 sigma. Now, one thing to note here is that with the DR2 release of DESI BAO data, this significance has increased to 2.8 to 4.2 sigma. Along with that, there is another change, and that is that now just DESI BAO and CMB together reject the cosmological constant at 3.1 sigma without use of any supernovae data. So here the plots are with DESI plus CMB plus Union 3 in the DESI DR2 paper, which came out this year in March. And what we see is that a phantom crossing happening at a redshift of around 0.5. And this is supported by different kinds of parameterizations used, not just the CPL parameterization, which is quite popular, but also the other parameterizations. And what is interesting is that all of them show a phantom crossing close to a redshift of 0.5. And before that, before 0.5 of redshift, the dark energy was phantom in nature. And this is very difficult to explain theoretically. If dark energy was always in the quintessence region, or if the equation of state remained greater than -1, then it could be described by quintessence models or single scalar field models in quantum field theory. But that is not the case. We see that the dark energy density is going from dark energy equation of state is going from phantom to non-phantom, this transition. And we need to note here that this is an 8-parameter model. So this has 6 ΛCDM parameters plus the 2 W0W parameter for dark energy. Now, DESI also gave very strong constraints on the sum of neutrino masses. So for a normal hierarchy of neutrino masses, you need at least 0.06 eV, and for inverted hierarchy, you need 0.1 eV of total neutrino mass sum. But what DESI data in the ΛCDM models shows it as the bound is 0.072 eV at 2 sigma. So the inverted hierarchy is actually rejected at more than 2 sigma. Now this bound was with DR1, and with DR2 this has even gotten stronger at 0.064 eV. And this is only with CMB and DESI without any supernovae data. So another thing is that we have only an upper bound, and the posterior seems to be peaking at posterior probability distribution seems to be highest at sum of neutron mass is equal to 0. And if you actually extend this posterior probability distribution, it will sort of peak in the negative neutron mass direction. Now this is concerning because we actually expect to get a detection of non-zero neutrino masses in the positive neutrino mass sum region. So this is kind of concerning, and some people have proposed theories like neutrino decay, which will mask the effect of neutrino masses on cosmological data. Now, note that with dynamical dark energy, the bound relaxes to 0.2 eV. So it is not like with dynamical dark energy, that inverted hierarchy is rejected. But again, we do not see this posterior to be peaking in the positive mass direction. It's highest at the value of 0, even with dynamical dark energy. So this is concerning. Now, in our paper, what we did is consider a 12-parameter model. So we have the first 6 parameters of ΛCDM, then W0, WA from the CPL parameterization, which has this form as we have seen before. And we also have NF, which is the effective number of neutron-like species, sum of neutron masses, and also alpha S, which is the running of the scalar spectral index, and also ALens, which is the artificial scaling of the lensing amplitude. Now, alpha S is expected to be small but non-zero in even single-field inflationary models, and also ALens is important because CMB lensing is dependent on neutron masses, and Planck PR3 likelihoods actually preferred values of ALens much greater than 1, so that there was a 2 sigma tension, which we call the lensing anomaly. And we also include NF here to assess the situation of the Hubble tension in this 12-parameter model, because increasing NF increases H0 in the late universe, because it increases the energy density of radiation in the early universe, and that increases expansion rate in the early universe. And H0 is also correlated with W0, WA, and sum of neutron masses is also correlated with W0, WA, because these are all late universe phenomena. So varying energy density of dark energy will change the gravitational potential in the late universe, and that is correlated with sum of neutron masses, because neutrinos also become non-relativistic in the late universe, and more neutron masses will suppress the matter power spectrum, and that causes lower lensing of CMB photons, and that is why this ALens parameter is correlated with sum of neutron masses. So our main goals of this paper, of these 2 papers, were to check whether the preference for dynamical dark energy survives in this largely extended parameter space. So we need to check that if we just do simple extensions to the 8-parameter cosmological model considered by DESI, and if we can still see a preference for dynamical dark energy. We also want to provide a reasonable bound on sum of neutron masses parameter, because this bound is very strong in the ΛCDM model, and we want to consider the possible correlations with W0, WA and the ALens parameter, so that the bound we get from this 12-parameter model is more robust compared to a ΛCDM model, because the data seems to be preferring a dynamical dark energy model. Hence, we need to question if the bounds from ΛCDM are certain or not, or how relevant they are. Now, we also need to give a definitive answer regarding the lensing anomaly in a dynamical dark energy scenario, because the previous studies only did evaluate the lensing anomaly in the ΛCDM model. And we also want to use the Planck PR4 likelihoods, because they have shown much less lensing anomaly in the ΛCDM model compared to Planck PR3. In fact, the lensing anomaly is less than 1 sigma, which means that the lensing anomaly is not there in the Planck PR4 likelihoods in the ΛCDM model. So we'll use the Planck PR4 likelihoods too, because we feel is better for the determination of sum of neutron masses as well. And we also want to assess the level of Hubble discrepancy in our 12-parameter model. We do not expect to resolve the Hubble tension, but we want to see that how far it can be reduced, and if the Hubble tension is robust in this 12-parameter model or not. So we use these datasets, Planck PR4 for CMB. We use the helipop and lollipop likelihoods along with Commander for low multiple temperature data. And we use CMB lensing data from Planck PR4 and Atacama Cosmology Telescope data release 6. We use BAO data from DESI. So in the first paper, as I said, we used the data release 1, and in the second paper, we used the data release 2. For Supernovae, we use the 2 datasets, Penton Plus and DESI DR1 we do not use Union 3 because it produces results in between these 2. So we are considering the 2 extremes, Penton Plus and DESI DR1 and we also use the weak lensing data in the second paper, which we did not use in the first paper. So this is dark energy survey year 1 results. So we note here that Penton Plus and DESI DR1 supernovae have some supernovae in common. So we cannot use these 2 datasets together. We have to use them separately to avoid any double counting. So our first result, our main result of the first paper was this plot in the W0 WA plane. What we saw is with Planck data or Planck with lensing, these black and the green contours. So there is no proper constraint on this WA parameter, and also W0 is quite the bound is very relaxed on W0 as well. So we basically do not have proper constraints on the dynamical dark energy parameters with Planck data alone. And with DESI, the bound improves a bit, but still for getting good constraints on the W0 WA parameter space, we need the supernovae data as well. And we find that with Penton Plus and combined with CMB and DESI, the cosmological constant is still included within 2 sigma, whereas DESY5 actually rejects the cosmological constant at more than 2 sigma. So now DESY5 supernovae might have some systematics as discussed in this paper by George F. Statiu. And so what we basically find is that with Pantone Plus, the cosmological constant is not only the cosmological constant is included within 2 sigma, we also have some quintessence parameter space. So this parameter space between this vertical line and this slanted line is for quintessence, where the equation of state of dark energy always remains greater than -1. And we see some quintessence parameter space to be allowed by the data as well. So our conclusion was that the evidence for dynamical dark energy is not yet conclusive, and it's really dataset dependent. And in the second paper with the DR2 likelihoods, what we find is that the cosmological constant is still allowed just at the boundary of the 2 sigma contour for Pantone Plus along with CMB plus DESI DR2, whereas DSY5 actually rejects it at more than 2 sigma. So again, we can say that the evidence for rejection of cosmological constant or evidence of dynamical dark energy is not yet conclusive, and it is actually dataset dependent. If you use DESI5, you'll get a detection of dynamical dark energy, but not with Pantone Plus. And we also see some quintessence or non-phantom parameter space to be included even now with Pantone Plus. With the neutrino masses, we got some very interesting results in this 12 parameter space. In the first paper, what we found is that there's the peak happens, the posterior peak of neutrino masses happens in the positive mass range for all the dataset combinations, and we actually got 1 sigma detection in 3 cases, including CMB plus DESI plus DSY5. And so with Pantone Plus, we had found this bound of around 0.3 eV, and also with DSY5. So we proposed this bound of sum of neutrino masses of around 0.3 eV as a robust bound for cosmology and particle physics. And since we see posterior peaks in all dataset combinations, it is actually it is actually a good thing, because we can expect that in future maybe we'll detect non-zero neutrino masses at more than 5 sigma. Now with the new DR2 DESI DR2 BAO, what we find is that the situation gets a bit worse as long as you use CMB plus DESI plus supernovae data. So with CMB plus DESI, we get this red contour, this red probability posterior distribution, and we see a 1 sigma detection, and we also get a peak with a peak in the positive mass range for CMB plus DESI DR2 plus DSY5, but we do not get the peak in the positive mass range for Pantone Plus. And actually, if you extend this, you'll get the peak in the negative mass range. So this result is slightly worse than the previous case. But if you use the weak lensing data, we need to note here that weak lensing data does not remain in a very significant tension with CMB plus BAO plus supernovae anymore in terms of the S8 parameter. In fact, the S8 tension has reduced to around 1 sigma with the weak lensing data we considered, which is DESI DR1 data, and it's around 1.4 sigma with the newer likelihood, which is DESI DR3 data. So we can combine this weak lensing data with CMB plus BAO plus supernovae, and then what we see that due to the lower S8 values, we get actually a 2 sigma detection with CMB plus BAO plus DSY5 plus weak lensing data, which is a 2.1 sigma detection at a mass of around 0.19 eV plus 0.15 minus 0.18 at 2 sigma. Whereas with Pantone Plus, we get around a 1.9 sigma detection. So as you can see from the red contour, this is the one with DESI DR5, whereas with Pantone Plus, we get the black contour here. Now, so this is quite interesting, because in future it might be possible to get a 5 sigma detection with futuristic datasets. Now with lensing anomaly, what we find is that the weak lensing data actually prefers higher values of A lens. So with CMB plus BAO plus supernovae, A lens is still with so there is a shift in A lens towards the right. So it's actually not consistent with A lens equal to 1 at 1 sigma, but it is still consistent with A lens equal to 1 at 2 sigma. But that changes when we include the weak lensing data sets, this red and green contours. And then what we see is that A lens equal to 1 is rejected at more than 2 sigma with weak lensing data. So this is for the first time with Planck PR4 likelihoods, we show that the existence of the lensing anomaly can depend on non-CMB data sets. Previously with PR3 likelihoods or the Planck 2018 likelihoods, you see the lensing anomaly even with just the CMB data. But here with PR4, we do not expect a lensing anomaly in the dataset, because PR4 has actually higher sky fraction, and as well as lower, less than 1 sigma lensing anomaly in the ΛCDM model. But here we see that with the weak lensing data, the lensing anomaly is more than 2 sigma again. So this is a significant result, because we cannot say that we have gotten rid of lensing anomaly as of yet, because we see its existence with the weak lensing data. Now, for Hubble tension and the Hubble constant, what we find is that with Planck datasets, this is from the previous paper, we see that from the Planck dataset or the Planck plus the lensing dataset, we do not get any constraint on H0, because H0 is very correlated with W0WA, and W0WA parameters are unconstrained with CMB dataset alone. With BAO, including BAO, we get some detection, but we need the supernovae dataset to properly constrain W0WA so that it breaks the degeneracy between W0, W and H naught so that we can get a detection. And still the value is around 68. And in the first paper, we saw that the Hubble tension persisted at a level of 3.2 to 3.9 sigma with CMB plus BO plus supernovae. But if you use DESI DR1 BAO in the second paper, we see that the tension persists at a higher level of 3.6 to 4.2 sigma. And weak lensing data has minimal effect on this. So this result does not change. So we can say that the Hubble tension persists. Hubble tension is robust in a 12-parameter model, and we actually need new physics to solve the Hubble tension. And the extensions considered in this paper is not enough to solve the Hubble tension. Now, for SA tension, what we find is that in the first paper this with CMB plus BO plus supernovae, the tension is at the level of 1.4 sigma with DESI DR3 weak lensing data. So the weak lensing tension or the SA tension is actually less than 2 sigma now. It is not a serious tension anymore. Previously with Planck PR3 likelihoods, this tension was at the level of 2.4 sigma, but currently with Planck PR4 likelihoods, this is actually less than 2 sigma now. So here we also see some so these plots show you the correlation, 2D correlation plots between various parameters. And what we find is that WA and sum of neutron masses are very highly correlated negatively, whereas there is a positive correlation as expected with A lens. Whereas S8 and sum of neutron masses are strongly negatively correlated, and the weak lensing data actually prefers lower S8, and that is why it actually prefers higher neutron masses, and that is why you get a detection when we include the weak lensing data. So to summarize, given that CMB plus BO plus Pantheon plus dataset allows the cosmological constant at the edge of the 95% contour or the 2 sigma contour, we can say that the evidence for the dynamical dark energy component is dataset dependent and not yet conclusive. So we got a 2 sigma detection of non-zero positive neutron mass sum. The peaks in the sum of neutron mass posteriors indicate a promising trend towards a possible 5 sigma future detection of non-zero neutron masses. And we recommend this bound of 0.19 plus 0.15 minus 0.18 eV. This bound at 2 sigma is used by the cosmological and particle physics communities as a reference. The lensing anomaly with the weak lensing data suggests that even with Planck PR4, the existence of the lensing anomaly could depend on non-CMB data sets. And we also find that simple extensions to ΛCDM explored in this study are insufficient to solve the Hubble tension below 2 sigma level. So we need possibly some new physics to solve the Hubble tension. Hubble tension is robust as far as this 12-parameter model is concerned. The SA tension with DESI DR3 analysis is reduced to 1.4 sigma with CMB plus BO plus supernovae data. So the SA tension is not a very large tension anymore. Thank you.